Thank you. I am starting with a video because I always like to make sure we're talking about the same thing, and a video is a good way to do that. So I would like to talk about wave-ice interactions, but in particular, what the wave and the momentum and energy that's carried by the waves into the MIZ, what I think that maybe means for the rest of the MIZ, the rest of the system. So not just waves for the wave's sake, although I love them, but waves for more of this, air ice ocean system, what maybe it means. And I know we have all these definitions of the marginal ice zone. Here, I'm sort of showing you this video to lean on the conventional definition of that the MIZ is where the waves are affecting the ice. And so certainly in this video, that's what you're seeing here. This video is just looping. It was collected from an icebreaker just at the ice edge in the Beaufort Sea. So there's wind and waves out here in open water, and then those waves are propagating in, and you can see a lot of motion in this broken brash ice at the edge. And then even just a few hundred meters in, you see, if you look in the foreground, there's not as much motion. So in this case, there's very rapid attenuation of this wave energy coming into the ice. And my point really is that as the waves propagate in and they attenuate, uh, that some of the momentum they were carrying and some of the energy they were carrying must be transferred to something else. It's no longer carried by the waves. We can argue a lot about all the details of the physics, but it must be going somewhere because it's not present in the waves anymore. I think that's interesting for the rest of the wave ice ocean atmosphere system. And I think it's particularly interesting because it's a remote source. We often think of things happening in the MIZ as a 1D balance that's happening in the vertical at a given location, right? There's sunlight coming in and there are all the heat fluxes, and that's all happening at one spot. And waves are really something that comes in laterally. It's carrying all this energy and momentum from somewhere else in the domain, maybe from, very far away in the Southern Ocean if you're talking about the Antarctic MIZ, or maybe from regionally if you're talking about the Arctic MIZ. So I think that's interesting. So I'm going to start with a case study to kind of map out what I mean by the energy and momentum that's carried. This case study was a short experiment that we conducted at this ice edge here. So open water and then ice. This video that's looping very quickly, which I'll pause for a second here to show you what I mean. This shows you the domain, which is only about 5 kilometers by 5. Oh, sorry, this is 10 by 10 kilometers here. Where the gray is the ice, which we mapped with the shipboard radar. So we have a good accuracy on that. And you can see the radar footprint move along throughout this movie. The movie spans about an 8-hour experiment. We put a few buoys out in open water and we put a few buoys in the ice. These are the Swift buoys that you see here that we make in my lab at Applied Physics Lab, University of Washington. And in addition to making a wave measurement, they measure the atmospheric fluxes, the winds, and then they measure the turbulence in the water, which is a unique capability that'll come up in a second here. And what was interesting about this experiment was instead of having the waves coming normal to the ice, which is sort of the cartoon we often have for an MIZ, or is what we teach in a classroom, these waves were very obliquely incident to the ice. You can see my arrow here and my little coordinate system here. But don't trust the arrow, trust the directional wave spectrum measured by the buoy that was out in open water. So here's where the color is the log scale of the energy, the radii are the frequencies, and then the theta is the direction. So the waves are coming from the east southeast, and they're approaching very obliquely. And if you play the movie again, you see that these dots where we put the buoys out, they start here and they go sort of down wave direction. And that's the point here, is that there's some motion in the ice edge that's associated with that wave forcing. So first we did the very conventional thing, is just looked at the wave attenuation into the ice. So that's what this plot is. It's making a composite over several buoys that were put out. And the x-axis here is the distance in meters into the ice. So 0 is the ice edge, and then this would be 1,000 meters into the ice. And this is just the wave height. Of course, the attenuation is actually a spectral quantity, but I'm just using wave height to make it easy. The dots are all the observations from the buoys that were within the marginal ice zone, right near the edge. And then the dashed line is a conventional exponential decay of attenuation, from which you get an attenuation coefficient. So that's all very conventional. What was interesting about this study is that we looked at the motion of the ice and the motion of the buoys. So considering the buoys a Lagrangian tracer for the ice motion, but also being able to map the ice motion with a radar, which is where this shipboard radar is such a wonderful tool that you can basically use an optical flow or particle image type techniques to map the ice motion. And here's the ice motion plotted in a similar coordinate system, the distance into the ice, and it's the velocity in the along ice direction. And you can see there are very strong velocities right at the ice edge, and they also decay rapidly into the ice. And that decay looks something like the wave height decay. So this paper is a 2021 paper where we walk through a momentum balance and demonstrate that the gradients in the flux of momentum carried by these waves is a good explanation for the motion that occurs in the ice. So these is wave-driven ice transport, and it's really the gradient of the radiation stress, we call it, in the wave field that is driving this. But there's also winds. And every time I present this, people say, well, wait a minute, the winds move the ice. Of course the winds move the ice, but they move it on a very large scale, and they don't have these kind of sharp gradients. So I would say here that the winds are this background motion because this doesn't decay to zero further inside the marginalized zone. It decays to some background level. That background level turns out to be about 3% of the wind speed. So we feel good about that. That's convention. So at the very large scales, yes, all of the ice flows are moving with the wind at about 3% of the wind, turning to the right a little bit, et cetera, et cetera. But right at the ice edge, where there are strong gradients in the waves, there's additional motion that's driven by the waves, and that maps out pretty well. So I think that's something that hasn't been talked about much in the literature, and I think is important as a transport mechanism. And then I think it's also related to the energy. So this was momentum because that's what drives transport. But if you look now in the thin layer of water surrounding all these buoys and the brash ice they're in, and you look at the turbulent dissipation rate measured by the buoys, and you do it in the same form of in the distance into the ice, you see these really elevated levels of turbulent dissipation in the water, and those are also rapidly decaying into the marginal ice zone. And these, you can also do an energetic balance here and say, well, the gradient in the energy flux carried by the waves, that would have the same units of a dissipation rate. So if you accept the hypothesis that much of the wave energy that comes into the MIZ is lost by generating turbulence at the ice-ocean interface, this is evidence for that. And it, at least within an order of magnitude, it pencils out that it's the d by dx of ECG from the waves is about the same as epsilon here, integrated over depth. And here we integrate over 2 meters because that's all the observation we have. But the layer of ice and water here, the brash ice, is about 1 meter thick or so. And so each piece of ice, as it moves with the waves, is scrubbing on the water around it and below it a little bit because it has a little bit of its own inertia and added mass as it moves around in the waves. So it will make these little bits of shear with the water around it, and that drives turbulence, and that's a loss mechanism. Of course, there are also ice collisions, and if it was an ice sheet, there'd be all this things happening there. But this ice is already all broken up, and there's not a lot of collisions happening, or we think collisions are a smaller term. So okay, so that's a case study trying to explain what I mean when I say the waves bring momentum, which means transport, into the marginalized zone, and the waves bring energy, which now I'm showing means turbulence in the ocean, which is a mixing process, right? That's a way to mix heat and any stratified layers that are forming just below the MIZ. So that's just one case study. That's only 8 hours of data. I've been thinking lately about what this means for a larger scale system. So I'm going to reach into this data set we've been collecting for now 12 years. It's in the Beaufort Sea, just north of Alaska. So here's Alaska, there's the North Slope. And these are the two mooring locations. They're at 74 and 75 degrees north, respectively. And here's just an example of what the ice looks like late in the season on a given year. I think this is 2020. Some years, like this year, the ice edge is way up to 80 degrees, and this is all open water. So it varies. These moorings have been maintained by the Woods Hole Oceanographic Institution for decades. And in 2012, they offered us to add wave sensors to the top of the mooring. The mooring is a subsurface mooring. So we use a Nortec AWAC that looks up with a up-looking sonar beam, measures the ice draft, and measures the waves. And so we have had that collaboration going since 2012. It's a nice long data set. Here's an example of it. Here's what the top of the mooring looks like. There's the instrument that looks up. So this is a schematic of how that works. And then here's all the data. over the last 12 years. Significant wave heights, and the two different moorings are shown in blue and green, and then ice draft. So there's this very strong seasonal cycle. And then some years we have waves and some years we don't, because some years it's fully ice covered, even in the summer at these locations, and some years it's not. And some years the instrument fails. We've, out of a total of 12 years, we've had respectively 1 and 1.5 years of failure at each site. So not too bad if you play this game long enough, things are going to happen. Here's a composite view of the overall seasonal cycle. So if I take all those 12 years and I just overlay them to see the seasonal cycle and have a lot of scatter, you can see the ice thickness grows throughout the winter season, peaks sometime in the spring, and then comes back down, things melt, and then the wave activity picks up in the summer and grows throughout the fall. And peaks sometime in the mid-fall. And this is a well-known effect that's basically just the fetch. If there's more open water space, you get bigger waves for the same wind forcing. There's a lot of interannual variability, but it's a big data set within to look at things. And I highlight it because it's all public, and I would really love more people to be using this. So here's some information on it. You can always get in touch with me, but there's a link for it. I am in the process of making netcdf files because I've been scolded about these MATLAB files repeatedly. So I'm working on that. And there's there's a lot of data available, and I'd love people to use it. Okay, so here's a thought experiment with that data. If I take the wave heights measured and I use that as climatology, and I say, well, given literature values for attenuation coefficients, how far would those waves make it into the marginalized zone on any typical set of conditions in the Western Arctic? And so I do a bunch of different cases for waves that are anything from 0 to 4 meters significant wave height. I actually do this thought experiment in the spectral form, but I'm just showing you the wave height form because that's easier visually. And so the waves, if they're big waves, they take 50 to 100 kilometers to decay into the marginalized zone. And if they're small waves, they decay within maybe 10 kilometers or even 1 kilometer. So, it depends. And you can zoom out a little bit and say, well, if I did this down in the Antarctic marginalized zone, it might be several hundred kilometers, right? 2, 3, 4, 500. I think the literature has things up to almost 500 kilometers now, which is really spectacular. But if the waves are big enough and the ice type has a low enough attenuation rate, they can go very far. But this is a little bit specific to the Western Arctic. So let's say 100 kilometers is sort of the cutoff. And so there's no waves past there. I'll revisit that in a moment, but for now, there's no waves past there. So this is the wave-driven marginalized zone of the Western Arctic is order 100 kilometers. What happens in that 100 kilometers in terms of the momentum and energy that's brought in by the waves that are propagating and attenuating as they propagate into the MIZ? Well, here's the momentum. This is using the formulation that I was just talking about in the case study. So it is the gradient of the wave radiation stress. This is the tensor, so it has a cross ice flux of along ice momentum, and it has an along ice flux of cross ice momentum. So you do it each of these different ways, but it basically scales with the wave energy. So you can approximate it in this way, and you can get something that looks like a stress, and that's great because you can compare it with the winds, and that's what I've done here. So these black lines are the decay of, or the amount of momentum that's being released by the waves as they attenuate going into the MIZ. And then the colored lines are a constant wind over the entire MIZ. So it has no gradient because it's just a large atmospheric synoptic forcing that's everywhere. And how strong those winds would be, what that wind stress would be. And then you can see the amount there, and this is the wind level in meters per second. So 14, that's the dark red, that would be 14 meters per second, 30 knots. That's really strong winds. That's this line up here, right? It's strong forcing everywhere. And I'm just trying to compare, how much do the waves matter relative to that? And here you would need very strong waves, and you would only be seeing a wave effect that was significant relative to the wind in the first 5 or 10 kilometers of the MIZ. But if you had lower winds, you can see that these two things start to intersect further and further to the right. So these wave effects might be important maybe 20, 25, 30 kilometers into the MIZ relative to the wind. And the point is that this is a localized effect near the ice edge where the attenuation is happening, and it's distinct from this wind-driven thing that's on a much larger scale. You do the same thing for the energy, and do that same idea that the loss rate is the gradient in the wave energy flux, and that becomes like a work rate basically, and you could compare that to the work that's typically done by the wind on the ocean, which is usually coming through in the open water case. That's usually coming through wave breaking that is driving lots of turbulence in the ocean. But in the MIZ, there's really usually not much wave breaking anymore because the waves have been attenuated and smooth, but there's still wave activity rolling through, and that's driving. It's a different mechanism to drive turbulence in the upper ocean. So I'm making a similar kind of comparison here. When do the wave contributions to that, the black lines, matter relative to the wind? And the answer is more or less the same. It's important very close to the edge, and it dies off because the waves are attenuating. It dies off within the first 50 kilometers or so. And this sort of 50-kilometer number is, I think, key because, for some models that may be subgrid scale. So there's two issues that are ripe for addressing in the future. Is most modeling systems don't have these two terms, additional inputs of momentum, which drives transport, and energy, which drives mixing, that are a wave driven contribution of that is missing from most models, and it may be happening at something that's at subgrid scale for a lot of the larger models. So how should we parameterize that? How should we include it? When does it matter? Those are the kind of things I'm thinking about here in these thought experiments. I don't have hard and fast answers for you on those, but I do think these two formulations are a reasonable approach, and you can do them just by knowing the wave field out in open water, which we're pretty good at forecasting, right? WaveWatch 3, WAM, whatever you want to use. In open water, that works pretty well. And we have some constraints on alpha from the literature, and we have various wave ice formulations that are in, WaveWatch 3 and all these things. So you could be using those things just to know what the gradient of the wave field is. And then once you know the gradient of the wave field, you're off to the races, right? Because you're just d by dx of these wave quantities, and that tells you how much momentum and energy you're releasing into the marginal ice zone. So this is something that I think is tractable to include without a lot of additional work. Okay, so pause there and say, well, what about my idea that there's no waves, more than 100 kilometers into the marginal ice zone in the Western Arctic? There would be deeper in the Antarctic. Well, that's not actually true. There are some waves there, but it's a bit of a surprising answer. And there was this nice paper that one of CC students worked on with us. Vince Cooper did this as part of his master's, and I think he did a brilliant job with it. He used some of the data that I was just advertising, and he said, well, I want to look deep inside the marginal ice zone and see, do I ever see waves there? And does the model that I'm working with, reproduce that, make sense of that? And the spoiler is that, yes, there are waves there, but they're not quite what we originally expected. So here are some data from that data set in open water. So this is kind of the null case. Here are the wave heights and a histogram of them. Here's the wave spectra. So energy as a function of frequency. And then down here, this is a fetch scaling. This is trying to make sense of, does the amount of energy in the wave field that's over here on the vertical axis make sense in terms of what the scale of the waves is in terms of its frequency, its peak period. And so waves in open water, we have lots and lots of data and decades of research to know about how a wave spectrum evolves, and know that it should have this canonical shape to it, and it should have this peak. This is a little bit, in a very heuristic way, a little bit of an analog for the flow size distributions that have parametric shapes and self-similar forms. The waves also have this self-similar form like this. So we know what this should look like, and it should lie along this line, basically in open water. We then, Vince looked further into the ice, but only within the first 100 kilometers of the ice, and said, do I see waves in the first 100 kilometers laterally of the marginal ice zone? And yes, you do sometimes, but they're usually not very big. And they have this spectra that's kind of muted, and this is a busy plot here, but their self-similar form changes because of attenuation. And then down here, all the points lie below that 1-to-1 line. And that suggests that there's less energy than you expect given the wind forcing. And that makes sense, right? The waves are attenuating as they propagate into the ice. So they were made somewhere else, they propagate into the first 100 kilometers of the ice, and they attenuate as they go. So they always lie below the scaling line for open water waves, and they always have a shape that is muted relative to that. So then he looks more than 100 kilometers in the ice and says, do I ever see waves there? And the answer is yes, but this is the part that was initially surprising, is that those waves are always kind of small, and they look a lot more like open water waves. They lie along this scaled line. They have the canonical shape of the spectral tail. And these are there because the deep, greater than 100 kilometers into this marginal ice zone, there are still big stretches of open water. There are lakes and ponds and leads, but I like to think of them as lakes and ponds because it helps me picture these small waves being generated. And those, if these open areas are big enough, then you can generate waves locally. And this is an image. This is I think it's a RadarSat-2 image. Forgive me, it's not well enough annotated, but this comes from his paper. And the point is that there are these big stretches of open leads that are many kilometers. And, a 10-kilometer lake is big enough to make pretty big waves. If anyone's been out, canoeing or something and had a windy day on a lake, right? It can get, you can make 1-meter waves pretty readily, and they don't need a lot of time to do that. So I think the surprising thing is that there are waves way far back within the marginal ice zone in the Western Arctic, and they're just locally generated wind waves. They're not propagating in from the boundaries. And all of this is also probably a sub-grid scale process for most models, right? A lot of models would have to know this is there, this exists, that you have these kind of big areas of open water. And then whatever comes of this, right? These waves will then hit the edge of the ice here in the local sense, and they will also have some momentum transfer and some energy transfer that's here, and that's also probably not included in the models. So this is where we get to the intersection of maybe a different MIZ definition, because this also looks like an MIZ to me in this image. It is ice that is marginal, but this far into the ice, where you're not having waves from somewhere else propagate in, this is more of a thermodynamic marginal ice zone, right? The ice is all broken up and the melt ponds have all formed and drained, and this ice is just kind of soupy. And so you would say this isn't a wave-driven MIZ, but then if you have this process for small wave, short wave generation in here, maybe there are still wave processes that matter in this MIZ. So that's a neat intersection that we've been thinking about. Okay, the last part here, I wanted to talk a little bit about what happens near the coast as another thing that I think is a sub-grid scale process in the large scale models, and that is interesting to be working on. And then I'll wrap up after just 1 or 2 more slides here. Landfast ice is another thing that is sub-grid scale and is interesting. So here's one example where there's land. This is the coastline. Then there's landfast ice here. This is a RadarSat-2 image. And then there's open water here. We have a mooring for a whole year in open water and one under landfast ice. This open water is open water in the springtime, and this is 2020, May 25th, but it's covered in the rest of the year. So if you look at the annual time series, these 2 moorings have some wave activity in the fall. There's nothing at either mooring throughout the winter. And then in the spring, these gray dots come from this mooring. So wave activity picks up in the spring, but it doesn't pick up for another couple months at this dot. Sorry, the colors don't match. That doesn't happen until July. So this means this landfast ice is causing complete attenuation, 100% attenuation of the wave activity here, which I think is remarkable, but it's fast ice. So it's very thick, and maybe it's grounded, and there's just no chance for the waves to propagate through there. This has implications for the cumulative amount of wave exposure at the coastline. And this line here first is the accumulated one that is out here on the shelf. This one is this is the wave energy that's actually accumulating to the shoreline, to the coast where coastal processes occur, and it's half of that. And a lot of climate scale models don't have landfast ice at all as a parameterized process or as a form, and it's often only 10 kilometers in the cross-shore extent, so it may be sub-grid scale as well. So there are some studies now that are trying to make these long, 100-year kind of investigations of what's going to happen to Arctic coastlines. And I think if you don't know that landfast ice is there and don't have this very strong wave attenuation effect of landfast ice, then those projections are pretty flawed, I think. So I think this is an important process that, again, subgrid scale, how are we going to include it? Okay, the last thing I'll note is just some fun work recently using fiber optic cables to look at this landfast ice. This is, again, in Alaska. This is a seafloor cable that goes from the shore out onto the shelf, and you can use this cable to measure waves. Pretty exciting and fun work. Maddie Smith has been leading this work. There's a picture of us putting some moorings out underneath the ice to calibrate the cable. And then here's an example where there's, in the fall, there's some the main ice pack is forming. There's some open water, and then there's also new coastal ice that'll eventually become fast ice. And so if you get some waves that form in open water, that's these waves here. This is a long cable distance. So HS is 1 meter. They're not big waves, but they're waves. They come into the coastal ice and they attenuate and they rapidly go to 0. So there's that complete attenuation of wave energy. The wave heights are, as they come down, the wave period is filtered because of the spectral effects. So I think this is another exciting way to get more of this data and learn how to parameterize fast ice and put that into models. I think it's also a place where we can get away from doing the conventional thing of just fitting one attenuation coefficient to a wave ice study, because we know that's wrong. Right? I mean, we're not even sure it's exponential. Let's start with that problem. But we know if you just fit one alpha to a whole data set, then you're assuming all this homogeneity in space and time, and that's not right. But we've been forced to do that when you only put out 5 or 10 buoys. Now, if you have these measurements along a cable, you have the equivalent of thousands of buoys, and I think we can do a better job of that. So I just wanted to highlight this as a new technology for sampling the MIZ, especially close to the coast. Okay, I'm going to wrap up and hope that I convince you that waves carry energy and momentum into the MIZ. I know we've heard already about how waves can, change the flow size distribution and cause breakup. I think that's really important, and I'm excited about that work. But I want to highlight that waves do other things too. They can cause transport and ocean mixing within the MIZ, and I think we should be thinking about how to include that in models. I think this Vince Cooper result that waves are locally generated far within the MIZ is important. It's another subgrid scale thing that we should be thinking about. And then I ended with this bit about fast ice near the coast and how this is missing. Okay, take questions now.
Thank you very much, Jim. Any questions? Takuji, do you have a question?
Oh, for me? Yeah. I've got a quick question. Yeah. So I think this is maybe more of an advert than a question, but Sam Brenner, who you know very well, Jim, has recently done this effort trying to explain the local generation of wave energy with using discrete element models. And so we have a cool parameterization that if people are interested in can use in their models for actually simulating this effect, and the effect it has on like approach mixing. It's kind of a little bit of an aside, but a really interesting thing, that piece of work that he did. I
second that. That's excellent work, and I like the preprint you guys have up now too. Looking at this generation and trying to understand this image, right? What happens in an image like this? What is happening inside here? I'm glad you brought it up, and maybe we can drop the DOIs in the chat for that, because I'm really excited about that work.
Yeah.
Thank you. Chris, did you have a question?
Oh, that was me.
Yeah. Any other questions? Okay.
Can you hear me?
Yes.
Yeah,
yes.
Takuji. Hi, Takuji.
Hi, how are you?
Good.
Good evening. It's very late in Japan.
I was going to say, I'm impressed you're still here.
Okay. Yes, just to show. Hi. Okay. I have a question about the. It was an interesting talk, and about the momentum transfer to the ice. the fact that momentum is transferred to the ice means that the ice will move horizontally, and and the fact that I guess that implies that there will be horizontal gradient in the ice velocity. Yeah,
And I think I know where you're going, but keep going. Yeah.
Yeah, we will. But suppose if the wave is propagating into the marginal ice zone normally to the ice edge, the ice wedge will eventually move, I guess. So it gets the concentration becomes higher and higher because the mass has to be conserved, and so I would imagine that at some point the ice would stop moving, which means that at that point the ice concentration would not change. But so I probably think that the result of this horizontal motion, which has horizontal gradient, so velocity has a gradient, which probably means that the ice, like, I don't know, either concentration or thickness will change in space, and that probably may affect the attenuation rate as well. So alpha is no longer constant. And in your thought experiment, did you assume that alpha decay rate was a constant, or?
Yes. So in the thought experiment I did, I used the literature values. I mean, like 5, 10 to the minus 5 or something. I can't remember. I think I just made an average of all the things from that region.
Right.
But I think you're absolutely right. There's this temporal evolution of the system. If you just start from, a still MIZ, turn on the waves, then this transport mechanism will, in the across ice or across MIZ direction, will cause a compact marginal ice zone, right? It will take the sea ice concentrations and compress them all in one place, and you'll get higher concentrations and then probably higher attenuation that goes with that. And I think you'll set up some kind of balance as you probably could picture it as a pressure gradient that's a balance in a cross ice direction that is then set up, which is kind of like wave setup on a beach, right? It's a little similar to that.
Exactly.
And the attenuation will probably be much higher. And so you'll kind of end up with, you'll eventually achieve some steady state on that. But then, of course, in the span of time it takes to do that, the wave conditions will change and you'll never have real stationarity. So that's one thing. The other thing, though, is the other dimension, a long ice dimension, where I think maybe you can end up with something that is more of a steady state with transport if you were infinite in that direction. And that's really the example I was showing. Actually, it's in the paper. The cross ice part is in the paper, but the long ice part I think is maybe more fascinating, or to me at least, that you get this strong flow along the ice edge. Where you're transporting ice in that direction, and as long as the ice edge is long enough, you're gonna just keep doing it. And then I think the balance you achieve is with some drag, interfacial drag between the ice and or the slurry of ice and water, and then the ocean below it. And so it's a different, balance you end up with. And the fascinating thing there is that you have, as you mentioned, these big gradients of velocity. That's a big lateral shear. That's a great engine for instabilities. Right? And we do see at the edge of a marginal ice zone, you see lots of swirly instabilities and eddy activity. And there are lots of reasons for that, right? There's a whole other zoo of, physical oceanography things happening there, where you have lots of baroclinic things in the ocean. But I think this is another process by which you get strong shear at an ice edge. And then that can cause all sorts of shear instabilities and the flow to roll up and do whirly gigs and all sorts of fun things to happen. That was a big part of that paper originally, and then reviewer 2 didn't like it and it died. But maybe we'll come back to it at some point.
Oh, okay. So, thank you. So when you mentioned about along the ice edge motion, it probably means that the angle of the wave penetration into the ice edge plays some role, right? I mean, there's definitely a difference between like waves propagating normally into the ice edge or like almost along the ice edge,
Absolutely, yeah. So that case study I did was, very oblique. That angle really mattered. And then, but in any given case, you want to generalize this, you just calculate the different terms in the radiation stress. So there's an SXY in the local coordinate system. There's an SXX, and there's an SYX and an XYY, right? There's all those different terms. So that's pretty tractable to calculate based on the, if you have directional spectra observations, or if you have a model, the model has all that. The wave models do.
Okay. Okay, great. Thank you very much. Very interesting.